This is the V-2, the world's first long-range guided ballistic missile. It changed warfare and pioneered the technology for space. On a pillar of fire, the V-2 launches skyward. Its powerful engine pushes it to the edge of space before beginning its descent. But this was a vengeance weapon. Traveling at supersonic speeds, it delivered its 1-ton warhead to distant targets. To understand this machine, let's look inside. Beneath its skin lies a complex structure, an engineering marvel that made its... The core is dominated by 2 propellant tanks, a network of pipes, and the engine. This layout became the blueprint for fuel. The heart of the propulsion system was its advanced engine. It burned liquid oxygen and an alcohol-water mix to generate immense... When assembled, these components form a formidable vehicle. Each part worked in concert, creating a weapon that was a quantum leap in... The V-2 was an imposing machine. At 14 meters or 46 feet tall, it towered over a 3-story building. Its body was over 1.5 meters in diameter. For stability, it used 4 large tail fins, spanning a width of... Its impressive exterior hides a complex interior. Let's delve into the systems that made its flight possible, starting with... The rocket's airframe was a thin steel shell for aerodynamics, attached to an internal framework that supported the heavy internal components. Fully fueled, the V-2 weighed approximately 12,500 kilograms. The vast majority of this mass was... Let's take a sectional tour of the rocket's main compartments. The entire assembly is divided into key sections, each with a... Above the main propellant tanks lies the instrument compartment. This was the rocket's brain, containing the revolutionary guidance system. Below is the engine structure, but at the rocket's tip, housed in the nose cone, was its deadly purpose: the warhead. The warhead section carried the high-explosive payload. Its conical shape was crucial for stability during high-speed atmospheric reentry. Detonation was triggered by a simple contact fuse at the tip. Upon impact, this would initiate the explosion of the main charge. The warhead's main filling was amytal, a stable and powerful explosive, poured in as a liquid during manufacturing. It carried a payload of 910 kilograms, or nearly 2,000 pounds. The amytal mixture was 60% TNT. Behind the warhead was the instrument compartment, the V-2's nerve center. This section housed its innovative automated guidance system. Central to this system were 2 free-spinning gyroscopes. These devices provided a stable reference, allowing the rocket to maintain. By measuring deviations from the flight path, the gyros sent signals to the control system, which made corrections to keep the rocket on course. These signals were processed by a simple analog computer. This primitive electronic brain would calculate the necessary adjustments. Power for the entire guidance and control system was supplied by a set of batteries. These provided the electricity needed for the gyros. A central distribution panel routed electrical power and control signals, connecting all the separate components of the guidance system. Together, these parts formed an inertial guidance system, enabling it to hit a city-sized target from 300 kilometers away. The V-2 was powered by 2 liquid propellants. It carried a fuel and an oxidizer in separate tanks, which combined to produce... These tanks were constructed from lightweight aluminum alloy and integrated into the rocket's frame to save weight and maximize capacity. Pipes at the bottom of the tanks fed the propellants down to the engine and turbopump assembly in the rocket's tail section. This entire central structure, containing the guidance, propellants, and engine, formed the core of the V-2. Let's examine the propulsion system. Its engine was powered by a sophisticated turbopump, which fed propellants into the combustion. But power alone is not enough. The rocket needed to be steered. The V-2 employed a clever dual system for control during ascent, for graphite vanes in the engine's exhaust steered the rocket. In the upper atmosphere, aerodynamic rudders. This combination of thrust vectoring and aerodynamic control gave the V-2 remarkable stability and a degree of accuracy previously unseen in... The standard warhead weighed around 1,000 kilograms, or 2,200 pounds. This payload could be delivered to a max... To launch this weight, the engine generated 25 tons of thrust, burning nearly 9 tons of propellant in just over a minute. The turbopump forces fuel and oxidizer into the combustion chamber. They ignite, and the resulting high-pressure gas creates thrust. The entire burn lasted 65 seconds, accelerating the rocket to over 3,500 miles per hour before the engine cut out. After engine cutoff, the rocket would coast on a ballistic arc, reaching an altitude of over 80 kilometers before falling back to Earth. The immense temperatures and pressures inside the combustion chamber required advanced materials and an innovative regenerative cooling system to prevent melt. To withstand extreme heat, the engine used regenerative cooling. A portion of the alcohol fuel circulated through channels in the. This process cooled the engine structure to manageable temperatures while also preheating the fuel, which increased the engine's overall efficiency. At the top of the combustion chamber was the injector head. Its crucial job was to spray and mix the fuel and liquid oxygen correctly. The V2 used a plate with numerous small injector nozzles. This design ensured thorough propellant mixing, which was critical. The ignition sequence was a delicate process. A pyrotechnic igniter fired first, then main propellant valves opened in sequence. Any error in this sequence could cause a hard start, a catastrophic explosion on the launch pad, a common problem during development. Now let's look at the device that fed this hungry combustion chamber. The turbopump, another one of the V2's most advanced and critical. The V2 was one of the first rockets to use a turbopump, essential for delivering large amounts of propellant at very high pressures. The turbopump is two large centrifugal pumps, one for fuel and one for oxidizer, both driven by a single high-speed steam. Steam to power the turbine was generated by decomposing concentrated hydrogen peroxide, creating a high-pressure mix that spun the turbopump. Assembly is the heart of the engine's plumbing. Let's trace the flow of the fluids required for its operation. First, the fuel, a mixture of 75% ethanol and 25% water, is drawn from its main tank and simultaneously the oxidizer, liquid oxygen, is drawn from its tank and fed into the other side of the pump. The turbopump pressurizes both liquids. The alcohol mixture first flows through the engine's cooling channels before both propellants reach. The 25% water content in the fuel was crucial. It lowered the combustion temperature, which simplified the cooling requirement. The engine consumed these propellants at an incredible rate of 125 kilograms every second. Let's take a closer look at the forward, larger tank held the alcohol water fuel mixture. It was an unpressurized aluminum tank with fiberglass insulation. This tank contained the fuel, known as B-stuff, which consisted of 75% ethyl alcohol, or ethanol, and the total weight of the fuel load was approximately 3,710 kilograms, or just over 8,100 pounds. The aft tank held the oxidizer, liquid oxygen, also known as A-stuff, weighing around 4,900 kilograms. Now for the propellants that powered the turbopump. This system used a monopropellant and a catalyst to generate the steam needed to drive. A separate spherical tank held 175 kilograms of T-stuff, a highly concentrated 80% hydrogen peroxide. To decompose the hydrogen peroxide into steam, a catalyst was used. This was Z-stuff, a liquid solution of sodium. When Z-stuff mixed with T-stuff, it triggered a rapid chemical reaction, instantly converting the hydrogen peroxide into high-pressure steam. Finally, to ensure a steady flow of propellants from the main tanks, they were lightly pressurized using high-pressure nitrogen gas stored in. This entire intricate system of tanks, pipes, and pumps had to be transported to a launch site. The V2 was designed as its mobility made it difficult for Allied forces to locate and destroy the launch sites, which were often simple clearings in forests. For transport, the rocket was carried on a specialized trailer called the Vital Wagon. This trailer could navigate rough terrain to the entire convoy, including the rocket, launch platform, fuel tankers, and command vehicle, would travel to a pre-surveyed site. The primary mover for the convoy was the Hanomag SS-100 heavy tractor, a powerful vehicle capable of handling the transport trailer was more than a carrier. It was also the erector, known as the Meilerwagen. It also served. Upon arrival at the launch site, the rocket would be positioned over a simple, portable launch platform, or Brennstand. Using a hydraulic lift, the Meilerwagen would carefully raise the 12-ton rocket into its vertical launch position, a delicate Once vertical, the rocket rested on its launch table. This robust steel platform supported the rocket's weight and withstood the intense. The platform weighed over 1,600 kilograms. Its 4 adjustable legs allowed the crew to level it precisely on. The table could be rotated, allowing for fine adjustments to the rocket's launch azimuth, ensuring it was pointed accurately toward the target. In the center was a small, cone-shaped flame deflector. This directed the initial blast of hot gas outwards, away from the with the rocket erected and platform aligned. Final preparations for fueling and ignition began. The setup process was the launch sequence begins with ignition. The propellants enter the combustion chamber, and in a controlled explosion, the engine. For crucial seconds, the rocket is held down as the engine builds full thrust. 25 tons of force strain against the launch. With the engine at full power, the hold-down clamps release, and the rocket begins its ascent. The initial climb is slow as the tail fins sit nestled within the launch table structure, which provides final stability as the rocket lifts off the pad. Any umbilical connections that provided ground power or sensor data are disconnected as the rocket clears the immediate launch area. The rocket's target, often London, was approximately 200 miles away. The flight to this target would take only about 5. Let's review the internal sequence of events that leads to ignition. The entire process is a precisely timed chemical and mechanical. The process begins inside the turbopump steam generator. Here, the 2 key chemicals for powering the turbine are brought together. First, the T-Stoff or hydrogen peroxide is mixed with the Z-Stoff catalyst sodium permanganate. This creates an immediate. This high-pressure steam is directed into the turbine, causing it to spin at high speed and drive the main propellant pumps. Before launch, ground electrical power is supplied to the rocket systems through an umbilical cable, charging the internal batteries and running. Once fueled and verified, the launch crew retreats to a safe distance in a control vehicle to begin the final countdown. With the launch crew clear, the final automated sequence can begin, a process that will take the rocket from a standstill to supersonic speeds. From the control panel, the launch command is given. The first stage of ignition, or Vorstufe, is initiated. This command starts the flow of the turbopump propellants, T-Stoff and Z-Stoff, into the steam generator. As the chemicals mix, they produce the steam that begins to spin up the turbine, which in turn starts driving the main fuel and oxidizer pumps. The pumps begin to force the main propellants, alcohol and liquid oxygen, from their tanks and down through the main feed lines toward the engine. The turbopump quickly spins up to its operational speed of around 3,800 revolutions per minute, delivering the propellants to the propellants are fed at a specific rate and pressure into the main combustion chamber, ready for ignition. A pyrotechnic igniter in the chamber fires, and with the propellants now spraying in, combustion begins. This is the main stage. The temperature inside the combustion chamber skyrockets to 2,500 degrees Celsius, creating immense pressure as the propellant. This high-pressure gas is expelled through the engine's nozzle at supersonic speeds, generating the massive thrust required for liftoff. As the engine reaches full thrust, the rocket is released from the launch platform and begins its journey into the sky. Accelerating rapidly, the V2 climbs vertically for the first few seconds before its guidance system begins to pitch it over onto its programmed. As it gains altitude and speed, it continues to accelerate, burning through its fuel load in just over a minute. After engine cutoff, the rocket follows a ballistic path, coasting up to its apogee, the highest point of its flight, at an altitude. From its peak at the edge of space, the V2 begins its long, silent fall back to Earth, now an unpowered, streamlined bomb. As it re-enters the denser atmosphere, it picks up incredible speed, reaching 4 times the speed of sound. It would strike. While the V2 was a weapon of war, its pioneered technology, like liquid fuel engines and inertial guidance, became the foundation for the principles demonstrated in this primitive missile would be refined and scaled up, eventually leading to the rockets that would carry humanity to the moon. The V2 represents a dual legacy, a terrifying instrument of destruction and the ancestor of the modern space age. This guidance system, though primitive, was a marvel. It could steer a multi-ton vehicle over hundreds of kilometers without external command. As the rocket breaks the sound barrier, moisture in the air condenses around it, forming a vapor cone, indicating its immense. During the powered ascent, the guidance system is actively steering the rocket. It follows a preset program, pitching over at us. Let's take one last look at the guidance system. The gyroscopes maintain their orientation in space, providing a fixed reference. As the rocket pitches and rolls, the gyroscopic platform remains stable. Sensors measure the difference between the rocket's actual. This information is fed to the analog computer, which calculates the necessary commands to send to the steering vanes and aerodynamic rudders. This closed-loop feedback system continuously corrects the rocket's course, ensuring it stays on the programmed path until the engine shuts down. The gyros are the heart of this inertial navigation system, a technology that is still fundamental to guiding aircraft, submarines. Other components, such as accelerometers, were used to measure the rocket's velocity. Once a specific velocity was reached, this engine cutoff point was critical. Shutting down the engine at the precise moment determined the rocket's range, preventing it from. Once the engine cuts off, the rocket is purely ballistic. Its fate is now governed only by gravity and momentum. Coasting. The V-2 flight has two main phases: a 1-minute power descent and a 4-minute unpowered ballistic coast to the target. During its coast phase, the rocket travels above the bulk of the Earth's atmosphere, reaching the boundary of space and offering a brief glimpse. At its apogee, or highest point, the rocket is traveling horizontally for a moment before gravity begins to pull it back down, arcing its trajectory. Thousands of these missiles were launched against Allied targets, primarily London, Antwerp, and Liege, in the final stages of World War II. The impact of a single V-2 could cause widespread destruction. Its high kinetic energy combined with its large explosive warhead, as it re-enters the atmosphere, the rocket is unguided and unpowered, its engine silent. It is now simply a one. Because it traveled faster than the speed of sound, there was no warning of its approach. The explosion would occur first, This made it a particularly terrifying weapon, striking randomly and without any chance for civilians to take cover, causing thousands of The aftermath was one of utter devastation. Buildings were reduced to rubble, and the psychological impact on the civilian population. Despite its technological prowess, the V-2 was militarily ineffective and could not change the outcome of the war. However, after the war, both the United States and the Soviet Union scrambled to capture German rocket technology and personnel in operations like Project. Captured V-2 rockets and components were shipped back to both countries, where they were meticulously studied, reverse-engineered, and test-fired. The missile's complex production involved thousands of workers, including forced labor under horrific conditions in underground factories like. This captured technology formed the direct basis for the early rocket programs of the two emerging superpowers, kicking off the Cold War space. Early tests were often fraught with failure, as American and Soviet scientists worked to master the complexities of large-scale rocketry. However, each failure provided valuable data, pushing the technology forward and paving the way for more reliable and powerful success. The internal workings of the V-2, once a closely guarded secret, were now being dissected and understood by a new generation of engineers. In the Soviet Union, the V-2 program was overseen by chief designer Sergei Korolev, who would use its principles to develop the R-7 rocket. The launch of Sputnik 1 in 1957, the world's first artificial satellite, was a direct technological descendant of the V-2. In the US, V-2 designer Wernher von Braun and his team became central to NASA, developing the Saturn V rocket that took humanity to the moon. Thus, the V-2 rocket holds a complex and controversial place in history, a weapon born of war that inadvertently opened the door to the cosmos. Its advanced design, featuring a liquid fuel engine, sophisticated guidance, and streamlined airframe, laid the essential groundwork. From its violent origins emerged a technology that defined an era, enabling humanity to reach for the stars.